Good afternoon. Welcome to lectures 129 and 130. Today we'll, after a break of about 1 month, we'll resume the relationship between what? This one, the first one, epsilon BB and EBB. These are the two types of interaction coefficients. Both are self. One is epsilon type, defined as I have already here. It is defined by this epsilon BB. And what is EBB? Yes, definition you don't see, but I tell you, it will be actually where it is, where it is, right there, right here. This gentleman. It is written here. You cannot see there because it is actually above the focus. So it is here. What is EBB? Del log FB weight percent over del weight percent B under the limit of weight percent B is 0. This is EBB. So the relation between these two was the task. We actually found the relation between epsilon BB and EBB. What is the relation? Right in the box. EBB is atomic weight of A over 230.3, which comes from 2.303 times 100. Times 100. 2.303 times 100. So 230.3 times atomic weight of B, and this factor multiplied by epsilon BB. So this is the relation. Only thing that was not shown, and it is pending, and I started showing this part. Actually, let me quickly recap. Start the relation. This is the job. Relation between epsilon BB and EBB. Both are self-interaction coefficient. For the binary, actually, see, this is actually binary property. Let us study. Now that all defining relations are obtained, we are in a position to take up the relation between epsilon BB and EBB. These are called self-interaction coefficient parameters. Why I said parameters? This will be self-interaction parameters or coefficients. Parameters or coefficients. And in passing, we may note epsilon BC and EBC are called ternary interaction parameters or coefficients. Okay? So, but this we will discuss today later on. But now, for the time, let me finish this. So let us start getting the relation. Epsilon BB by definition is del ln gamma B over del XB and under XB is 0. This all discussed last class. So repeating this, recapitulating. What is gamma B? Ln gamma B is nothing but FB mole fraction times gamma B 0. You know 100 times. So this is written somewhere here also. I have saved this. FB mole fraction is FB 8%. Henrian activity coefficient. Mole fraction. Henrian activity coefficient and Henrian weight percent activity coefficient. Henrian mole fraction activity coefficient, Henrian weight percent activity coefficient, they are equal, they are identical, they are equal. Their value is gamma B over gamma B 0, all you know. So just substitute here, this you get. Then you break this log term is ln FB mole fraction plus ln gamma B 0 over del XB, you know, and this goes XB, when XB is 0, note this, when XB is 0, weight percent B also is 0. I have written somewhere, when XB is 0, weight percent B is 0, so I have changed to weight percent B is 0. Then what you are getting? Del ln FB mole fraction over del XB, weight percent B is 0, Okay. Oh, what is this? Uh, okay. Here, suddenly, why actually? I tell you what. I, this is this. I'm sorry. This should be xb is 0. I'm sorry. This will be with 5% b is 0 in the next step. Not here. Not here. Not here. Retain what you had here. Retain this xb is 0. Right. xb is 0. What should I write here? What this? Hmm. It is xb is 0 rather than what percent b is 0, but step by step. So then this is okay. Then you actually get this del ln hb mole fraction over del xb is 0, and this term is a constant. Gamma b 0 is a constant and it's not function of xb, so it is out del. So you have now next is from this 2.303 take out del log FB weight percent. Why? You know FB mole fraction is same as FB weight percent. So I have written in terms of FB weight percent over del XB. I am writing here changing to weight percent B. But XB is not weight percent B, but this. So I actually divide by del XB by del weight percent B to keep the expression same. And what is this? When XB is 0, it becomes weight percent B is 0 as good. This is xb is 0 and weight percent b 0 are as good because this is as good as this, because when xb is 0, weight percent b is 0. So these I have shown here. Note 1, fb mole fraction is fb weight percent, and you can interchangeably use this, and weight percent b is 0 when xb is 0. So you get here divided by. And now this is by definition. This is by definition is what? EBB. EBB written here EBB 2.303 divided by this is what x del xb by del weight percent b. I actually told you that this value, if you calculate, then it will be atomic weight of A over 100 atomic weight of B. I have written here proof given below. Proof given below, and this is the proof. So if given that this is correct, then what relation you get between this and this? EBB equals to this. This goes to this atomic weight of A over this 102.303 will be multiplied, this is divided by here. So 230.3 atomic weight of B and atomic weight of A goes top and epsilon BB. This is just from this you can figure out or juggle out this one. Okay, that's EBB on the left hand side and epsilon BB on the right side. This is the final, this boxed relation is the final form, and this was done in the last class. So I am repeating as the thing is this, I have one job that was not over, that is still not completed. What is this? dxb over d weight percent b. When weight percent b is 0, is nothing but atomic weight of A by 100 atomic weight of B. This I have to show. Let us start. So this actually I have one couple of lines I showed, but today I will show you completely that this is nothing but atomic weight of A over 100 atomic weight of B. Start. What I did, what I have done so far. What is XP? XP, you know, XP I wrote somewhere here it is written there. XP. Often we use this atomic weight percent B over atomic weight of A. I'm sorry, atomic weight of A weight percent B in the numerator over atomic weight of A weight percent B plus atomic weight of B weight percent A. These are done number of times, 100 times. So all done. So write this out. XB is atomic weight of A weight percent B over atomic weight of A weight percent B plus atomic weight of B weight percent A. So XB over del weight percent B under the constraint of weight percent B is 0. This is the definition. So now this is actually you want to differentiate. It's like actually it is a ratio. So denominator square. Oh, okay, by the way, still one more simplification. So we don't want to handle weight percent A and weight percent B together. We want to have only one. So weight percent A is nothing but 100 minus weight percent B. So this was shown in this step. So if it is 100 minus weight percent B, you get here weight percent B atomic in common weight in the denominator. Our numerator is okay. Atomic weight of A, weight percent B over weight percent B. See weight percent B atomic weight of A, and this is 100 minus weight percent B. So weight percent B in common, it becomes atomic weight of A 100 minus atomic weight of B. Okay, weight percentage is you see you do this 100 minus weight percent B. So weight percent B is common. So you have atomic weight of A minus atomic weight of B and 100 plus 100 atomic weight of B. So no surprise, this is there. There what else you want? What else you want? Okay, over del weight percent B. And under the constraint of weight percent B is 0, we went up to this and then we actually ran out of time. So this is the last line for today. So I will show you right here. So now take up. This is the differentiation. So it is like a ratio, ratio. So what is this answer? I gave a star here already. I am continuing with the star. Today first line I am actually hitting here. Okay, is what? Equals to, tell me, denominator squares. So write that out. Recall. So denominator square. So recall your relationship derivative of a ratio d dx of u by v. Recall is v d dx of u minus u d dx of v divided by v square. The denominator square u v. So this square, write it out. Weight percent. Sorry. Weight percent b times atomic weight of A minus atomic weight of B plus 100 atomic weight of B squared. Then the denominator term as is copied. Weight percent B, write this, weight percent B times atomic weight of A minus atomic weight of B plus 100 atomic weight of B. Okay, this is your V d dx of u means d weight percent, del weight percent or d weight percent of B of atomic weight of A weight percent B. So d weight percent B over this is nothing but atomic weight of A. V into atomic weight of A. V d weight percent of B, V d dx of atomic weight of B, V d dx of weight percent atomic weight of A should be multiplied. Actually, let me write this. Let us move on. Atomic weight of A. V d dx of u minus u. This one. This u means atomic weight of A numerator times the differentiation of the denominator with respect to d weight percent B. It is nothing but atomic weight of A minus atomic weight of B. That's it. And of course, you have to give a external bracket. Weight percent B is 0. And let us simplify. Now, weight percent B is 0 is very helpful. Very helpful. So, what is this? You just keep on writing. Weight percent B, if it is 0, then what remains? This term is off. Drops out. Okay, what remains? 100 atomic weight of B times atomic weight of A. So, let me write nicely. 100. This term is over. And here, this is 0. The whole term is minus 0. Out. Again, you see what? It is 0. So, right here. This is 0. Which way will be better? Which will be better? And this way not better. This will be this way better. Better. So, this is 0. What remains? 100 atomic weight of B squared. So, what remains? In the numerator, just atomic weight of A, atomic weight of A, and 100 denominator. In the denominator, atomic weight of B. This I wanted to show. This I wanted to show. Proof. This today I could not finish this last class. Okay. So proved. Is a proof? Proof. So today proof. So with this we have completed the first item. What is the first item? The relation between epsilon BB and EBB. If you ask me what is the answer, this is the answer. So let us remove this, and actually I will save this relation. Okay, and we'll at the end summarize the four relations. This is the first one. Now I will take up the second one. What is the second one? That will write epsilon BC and EBC. Both are ternary interaction coefficient. Only one is in terms of epsilon, another is in terms of E. The difference between epsilon and E, you have understood this is in terms of gamma B and XB, and this is in terms of FB and weight percent. And still another difference, this is ln log base E, and this is common log 10 base. Okay. Log F. So three differences: ln log gamma B FB weight percent. Gamma B is the Raoultian activity coefficient. This is Henryan activity coefficient weight percent type. And what else? Denominator with derivative with respect to XB. This is derivative with respect to weight percent. And still another, this is in the limiting value of XB is 0. Under the constraint of XB is 0 by definition. I discussed all the XB is 0 I have discussed at length. And this is instead of XB is 0 is what? What is weight percent is, right? So move on. Let me, okay, these are actually dried up a little bit. So I have to remove this one first. Then and I'll save this relation somewhere. So let me remove this first. The previous one. Okay. So first item over. Actually, this I wrote this 1 month ago. So this ink has dried up. So it will be little bit tough to actually remove this, but I am trying, and it will. So actually, as I tell you, next item would be the relation between today's. Actually, I am actually the kind of utilizing the time, giving you the topics or subtopics that I will be covering. One is, as I told you, the relation between epsilon BC and EBC. This will not be very difficult. In the same manner, we'll do it. This is okay, one thing. And still next, the third one, that is very lengthy. That is epsilon, both are epsilon. Epsilon BC and epsilon CB, the third. This four already actually now pointed out that in sequence we'll take up 1, 2, 3, 4. The relationship between interaction coefficients. So we are continuing on that topic, okay? And for this, it will be required, for the third one, it will be required to develop thermodynamic equation of consistency, thermodynamic relation of consistency, or relation for the thermodynamic consistency. Using that, we will get the relation between epsilon BC and epsilon CB. And obviously, what it remains, the fourth one is EBC and ECB. That is very easy. After all these three available, the fourth is damn easy. So these four will be shown today. Let us see how much we can do. Actually, this thermodynamic equation of thermodynamic consistency. Actually, I before I remove this, this is our. Shall I remove this also as well? This as well. Actually, I think you have got this. This as well. This as well. Ah, that's nice. That's nice. Only this is important. So one, the first one. What is the relationship? Shall I write somewhere here? Maybe here. Maybe here. The first one that we got here. E B B is atomic weight of A over 230.3 atomic weight of B, say iron, manganese, iron, silicon, okay, iron, phosphorus. So A is the iron, atomic weight of iron is 56, and phosphorus 31, silicon is 28, etc. Okay, this can be used for compounds also. If it is a compound solution, like say slag oxide, FeOMnO, then that will be molecular weight rather than atomic weight. Don't worry, this is very easy to follow. And then what I shall write? Epsilon B B. This is the one continued. You may give a bar here, a box here to fence it off. So this is the achievement, first achievement maybe. The topic is relationship between the interaction coefficients. Epsilon type, E type. 4 possibilities. First. Second, I will take up, but let me leave this freely now. Bappa, so my name is asked me, then also you will just notify me that you have come. So if it is okay, because I'm rubbing it very hard. It is displaced. Displaced, no, so stand if I and just 1 minute. I've already just so actually, and if just give me that signal me that you have come, and then I will if I have any message then this verification is a message, online message. Correct though? It's okay though, because it is so difficult to remove this. You wait a minute. So this 4, actually the first one is done, is over. So remaining 3, this is actually has been firmly fixed on. It's okay. It's okay. Thank you very much. Oh, okay. By the way, just check. This line has been removed. Is this line visible? Just visible, sir. Okay. Or a little above. Well, I have to. Okay. I have small space. So that's great. Is it? This is also visible. This is visible, sir. It can be lower further. Acha, I'm showing. I don't remove that. Yes, the middle line is also. Okay. Thank you very much. Okay. Everything is okay, though. Everything. The CB that question is not. No, that is from the very beginning. From the very beginning. These actually. Post thermodynamics of materials is visible. But we don't want anything. So thank you. Don't worry. This is not important. Second one. So first one is okay. Over. Second one. If you follow the previous classes, what is this? No, what else? Check. Okay. Okay, sir. It's okay, sir. Acha, that what it. It's okay. What a Papa. No problem. Absolutely. Thank you very much. And just time to time, you just signal me. Thank you very much. So next is second. Let us press is this is better like the way I have written here one. Same way first epsilon what epsilon okay ternary B C and E B C. This is the next topic. Okay. Start. What is epsilon B C? Start. The relations between this. Okay. Very good. Okay. So this is actually our topic epsilon B C and okay. So what is this? Tell me. Okay. For example, what is B? What is B? What is C? B can be manganese, C can be silicon. And what is A? Iron, solvent. So EBC is what? Del definition. Definition I have all given. All. Then I am proceeding. Del ln gamma B over del X C XB is 0 and what should I write? Should I write here XC is 0 as well. It is better I write here. Right. Both are 0 at the limiting values of this 0. Exact 0. This is epsilon. This is called ternary interaction coefficient. Unlike this, this is self. This is self interaction coefficient. Effect of B on B. And this is both. One is E type, another epsilon type. This is effect of C on B. Effect of C on B. Okay. On C, effect of C means effect of concentration of C on the activity coefficient of B. This also I said. Okay, so keep on without wasting time. Keep on. What is del ln gamma B is what? What recall is? Tell me is FB weight percent. I am not wasting time. I can write FB. What is gamma B? FB. I am very sorry. Gamma B 0. Take a look from here. What is FB weight percent or FB gamma B is? FB weight percent times gamma B 0. These are 100 times I have said. Okay, over what? Del XC. Del XC. And you can take this since you have already used the bracket. So you put this maybe this parenthesis XB is 0, XC is 0. What is this? Still another line. You use this del ln FB weight percent happy over del XC and give a bracket. Oh, sorry, XB is 0, XC is 0. And what is this? Oh, by the way, what is this I am writing? I am showing here. This is log product. Log product is nothing but ln FB weight percent. This step I missed actually, but it is so easy in high school step, high school log plus log ln gamma B 0. Now these I have retained. Gamma B 0 is what? This is a constant. So deeper. So note here. Note like last time, last case. Gamma B 0. What is gamma B 0? Gamma B at 0 concentration of B. In binary system may be. So definition cannot afford to forget. Avoid. So that gamma B 0 is a constant. Okay. It is giving temperature though. But that is implied. But gamma B 0 is constant. Shall I be able to write here? I don't think so. Is constant. What is the meaning of constant? here what is the application? Is not function of xc. Is not, is constant, is a constant, is a constant, that is not function of xc. So out, very easy. Next is what? Simplify. Keep on doing this. What is, you don't like ln, you like log to be consistent with the definition of eBC. D log FB weight percent, and you have actually 2.303 outside. And not only that, do another thing at the same time. XB is not the, XC is not the suitable form in the denominator. What should be? To be consistent with the EBC, what is the form? Weight percent. So D del rather, weight percent C, happy, okay. And then you give a bracket here. You have no difficulty that when XB is 0, in the form of weight percent, B also 0. So put it in here, change this constant in the form of weight percent, no problem. What you have done here, just you will get a 2.303 here, you get a 2, and log is covered, FB weight percent is covered. What is this? Then divided by, it was XC here, you are writing weight percent. Okay, so that we may express this in terms of EBC. But for this we have a compensatory term. What is that? Del XC over del weight percent C. Happy? Weight percent B, sorry. C is 0. Okay. Have I written here? These are ternary right here. At the very beginning, write this is ternary interaction coefficient, and these are self. I told this now many a time. I wrote also, but write here ternary. You are dealing with ternary system, ABC, iron, silicon, manganese, iron, manganese, carbon. This you are dealing with, here you are dealing with AB system, iron, carbon, or iron, manganese. So ternary interaction coefficients or parameters. Coefficients or parameters. Whichever you like. Okay, this is fine. Very good. These I tell you. What is this? Tell me. 2.303. Tell me. What is the name of this? What is the name of this? Is nothing but effect of weight percent carbon on. I am very sorry. Weight percent effect of C, component C on activity coefficient of B. Okay, that's right. So it is, what is the name? EB, effect of C, effect of C on B, effect of concentration of C on the activity coefficient of B. Here Henrian activity coefficient, and hence the symbol E rather than epsilon. Epsilon involves gamma, Reltn activity coefficient. Happy? Very good. So EBC, and this is included in the definition. Weight percent B is 0, weight percent C is 0. So this very nice. We are very close. Only this stands in the way. What this answer I am giving you, this is nothing but atomic weight of a 100 atomic weight of C. This I will prove again proof here below. But for the time you consider this is the correct. Then what is the answer? Hence, what you get? Tell me. EBC may be conveniently written on the left hand side. Is what? atomic weight of A 230.3 atomic weight of C epsilon BC, and that's it. I'll also again save this here. Okay, second one. Okay, but before this, one job on hand, that is one responsibility to show that this is to show del x C by del weight percent C under the condition of under the condition, very important, weight percent B is 0, weight percent C under this condition is what? As I told you, atomic weight of A over 100 atomic weight of C, to show this. To prove. Okay, prove. Start. What is this? Del x C weight percent C, weight percent B is 0, weight percent C is 0. What is this xc? You know what is xc? Del in the ternary system, xc is what? What is in the binary? What is the xb and weight percent B? Atomic weight of A times weight percent B. So here it will be del xc is what? Xc is what? Let me write here. I gave you previously. What is the answer? From this you can remember this. Sorry, you can derive this. I'm sorry, derive this. How? What is this? Atomic weight of C, since it is C here, weight percent A times weight percent B. This can be shown. Okay, xc interconversion of mole fraction and weight percent. The relationship, remember, xc is what? Remember, you know this, first class, xc and weight percent C. xc is weight percent C divided by atomic weight of C, and in the numerator divided by that numerator divided by weight percent C by atomic weight of C plus weight percent B by atomic weight of B plus weight percent A by atomic weight of B. If you do this, then you get to this plus atomic weight of, oh, I'm very sorry, here, right down here. Atomic weight of A, weight percent B, weight percent C, fairly long term, plus atomic weight of next sequence atomic weight of B times weight percent A, weight percent C plus atomic weight of C, weight percent A and weight percent B. In fact, the numerator itself. Yeah, this is your very good. This is your what I wrote, x del xc over del weight percent C. I'll give bracket here. If necessary, bracket here. Is okay. So this is fine. Very good. So lights are okay. Thank you so much. Okay. So and give, as you know, highly important. This is 1, give a bracket here, and then put a still another bracket, outside bracket, fencing under what? This. Very important. Weight percent B under the condition of weight percent, weight percent B is 0, weight percent C is 0. I think you can very easily follow and you can do yourself. So, is next step, very important. Next, very, very important. Tell me again, derivative U by V. Numerator, denominator with respect to 8% C is equal to denominator square. First is denominator square. So do this. So do this here. Denominator. Okay, very good, very good. So let me write denominator, lengthy though, but I have to write this. Atomic weight of A, weight percent B, weight percent C, keep on, plus atomic weight of B. Wait a bit. I made a mistake here. It is a good thing that I checked this. I am very sorry. I am very sorry. Very sorry, very sorry. Very sorry. This is weight percent C times atomic weight. This atomic weight will appear twice rather than weight percent will appear twice. It's a good thing that I checked. Atomic weight of A. Similarly, here, first time I am removing, start weight percent A, and atomic weights will appear twice. From this, you can convert conversion of interconversion of mole fraction and weight percent. Mole fraction and weight percent. It just very easy. Atomic weight of A, B. So next term, remove this plus weight percent B, atomic weight of A, atomic weight of C. Okay, and last is what we have in the numerator. Okay, each is taking turn. Okay, if you are interested. Since actually I have messed up, it is better I show you what is the rule. First class interconversion of mole fraction and weight percent, mole percent and weight percent, etc. What is this? Xc is what? What is this? Xc. Xc is what? Xc is what? Weight percent C. Weight percent C divided by atomic weight of C over sigma. Sigma this means 3 ternary each. So what is that? Weight percent A by atomic weight of A plus weight percent B by atomic weight B plus weight percent C by atomic weight C. Happy? I will get this. Certainly. You will get this. Do this, you get this. This is the principle. Recall. Note. First class of solution thermodynamics. So, anyway, I am very sorry. Complete this. Weight percent. Last is weight. This will come back. Weight percent C, atomic weight of A, atomic weight of B. No problem. It is better I get more space now for atomic weight of B. So what is this? Give a bracket here, top bracket, and the whole thing. Is weight percent under the constant of weight percent. I don't have space here though, so right here weight percent B is 0, weight percent C is 0. Happy? Now is okay. Now Remove this. As I told you, denominator square, this is denominator. Write this out. Weight percent A. Quickly, atomic weight of B times atomic weight of C plus weight percent B, atomic weight of A, atomic weight of C plus weight percent C times atomic weight of A times atomic weight of B squared. This next is U by B. B square B times ddx of U, or so B times. Write this out. It's very easy, right? Go lengthy though, but you start from this side. Weight percent A, atomic weight of B, atomic weight of C plus weight percent B, atomic weight of A, atomic weight of C, and last one weight percent C, atomic weight of A, atomic weight of B. Actually, in textbooks you will not get these derivations. I have to say this in textbooks. These derivations, so you get the answer, result, and this is how. Following this constant, I said constant is a big issue in thermodynamics. Use this constant, then only you will arrive here. This result is given. This result, no change. I didn't come across. Okay, thank you. Continue. Go to first principle. Follow first principle and go ahead. Go on. Derive yourself rather than someone is deriving it for you. Maybe, if possible, we will try to find a new derivation, new way of deriving, alternative way of deriving. In fact, today time, I don't know how much. In the next item, we will have this. Thermodynamic consistency will prove our method. Reltn showed his method, gave his method, but we will rather be happy with our own method. Sorry. So I am right, okay? So this square here, the first term as it should be, give a bracket here. B, as we call it, U by V d dx of U. And where is it? Del weight percent C of this is nothing but tell me atomic weight of A, atomic weight. Differentiation of this with respect to this. Next minus what? U. This term times differentiation of this term, opposite. So this term, let me write weight percent C times atomic weight of A, and then d weight percent C of del weight percent C of, I am not writing this. I am not writing. Del, what is this? Del of this? What is this term? This I am not writing. Which one? This one. You write. If I call it U by V square, oh, this will be removed. C, this is C. V ddx of U minus U ddx. This part I am not writing for some reason. Okay, and very well, you must put, as you have done all the time, what you will write? Weight percent, right here all the time. Weight percent B is 0, weight percent, C is 0. Now is the time. See, now you see simplification. You see what simplification you will get. You will be amazed to see the simplification. First of all, tell me one by one. Weight percent B, second term. Weight percent B is how much? 0. Gone. This term gone. Plus. Weight percent C how much? Gone. Weight percent A how much? A how much? 100. 100. Solvent. 100. Okay. And likewise, what is this value, gentlemen? Weight percent B? Gone. Weight percent C? Gone. And most importantly, here there was a differentiation. We don't care. Why we differentiate? When weight percent C itself is 0. Why? Out. So what is left? A very simple. Oh, by the way, you tell me what is this weight percent here? 100. So now simplify. Right, 100 atomic weight B, atomic weight C, 0, 0. Time here this plus. So out times atomic weight of A, atomic weight of A times atomic weight of B, and minus out. And here what is remaining? 100. Tell me, 100 atomic weight of B, atomic weight of C, the only term that is left in the denominator, and with the square. Happy? What is this? This and this exactly same. So what is cancelled to? 100 atomic weight of B over atomic weight of C. This square. What remains on the top? Atomic weight of A, atomic atomic weight of what? What is this? Atomic weight of A, 100 atomic weight of C. Proved. And we are happy. Proved. To prove atomic weight of A over 100 atomic weight of C, and we have proved, which we have utilized, which you have which you have implemented. We put in here, substitute this result here, and this is the final outcome. So this answer is correct. That means this proof is valid, and this use is valid, and this is the final answer. So can I summarize here? This one, second one. So second out. Third, fourth. Third will be started today. 1 hour still we have at 1 hour roughly. So we'll work with this. So third, before the third, let me remove this and just here, just for the purpose of saving what we achieved. This one, right? 1. So write 2 maybe. 2 not bad. Here I am utilizing this space rather than this space. Okay, so what is this? eBC is what? Atomic weight of A by 230.3 atomic weight of C times epsilon B, C. Maybe a box. Sorry. 1, 2, 3, 4. 3 next. Third. What is that? That is both, this time both are epsilon. Epsilon BC and epsilon CB. Both ternary. Both ternary. You know this. In fact, these are ternary. But both are epsilon type. And you know what is epsilon. I have explained. If it is epsilon, then what? Anyway, you know, gamma will feature. Gamma will. And mole fraction will feature. In short, effect of C on B, effect of B on C. Both ternary interaction coefficients. So this is a job, lengthy, pretty lengthy, because to achieve this, we have to establish the equation for thermodynamic consistency in the ternary system. Remove this, all done. Bapu, Bapu, Appa, hello, come on in. দেখতো বাবা এই যে নড়ে গেল কিনা হ্যাঁ ঠিক আছে এই টপটা ঠিক আছে তো এখন বস্তু হচ্ছে হ্যাঁ এরকম কিছু একটা হয়েছে দেখ ভাই বেশি চলে যাবে আসছি আমি অনেকটা মেনে নিয়েছি এখন পুরনোগুলো চলে গেছে নিচেতে এসছে নিচেতে আচ্ছা দেখ তো দখল আমি এখানে হাত দেবো এখানটায় দেখ তো আর কি তার অসুবিধা কি আছে উপর লেখাটা ঠিক আছে কোর্স টপটা দেখবে এই লাইনটা একটু দেখবে খালি বেশি দেখতে হবে না এই লেকচার টেক্সচার সব ঠিক আছে তো আর এই যে লাস্ট লাইন I have actually just now write এখন দাঁড়া স্টে ব্যাক ওয়েট টু জাস্ট একটুখানি এটা মুছে দিচ্ছি একটু চেষ্টা করছি বাট আই থিঙ্ক নো সামটাইমস দিস হ্যাপেন্স অ্যাকচুয়ালি না if you give time actually no or just spend time then what happens is becomes very difficult to 1 hour 4 minutes it's okay that time is okay we are going very very slowly so that the things are clear to everyone. These are derivations, you cannot jump steps. So this anyway, thank you. It's okay though. I'm writing here. It's okay though. It's okay. Is it here? I'm writing. It's okay. This is one line I wrote. It's okay though. Because distortion, but tilted. Nothing. Thank you very much. I'll go slowly now. Both ternary interactions start. So 2 yes, as you know, it's better write this way. Let us have this as a prerequisite, as a prerequisite to establishing the relation between the two Ternary interaction coefficients two means which two? This. What is required to ternary? We have to establish. We have to establish the condition of thermodynamic consistency for the ternary system, for the ternary system for the ternary system 1, 2, 3, representing since we are using BC, but we are here using 1, 2, 3. Okay. Actually, in principle, when you know the principle, you know perhaps. No? If it is binary, you use AB. Binary system AB. Representation of binary. Not 1, 2. 1, 2. Maybe, but you can we use AB for ternary and above. 1, 2. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5. Normally, this is. So 1, 2, 3 representing ABC. ABC, okay, you know, ABC, where A is the solvent and BC are solutes, okay, and 1 is the solvent, 2, 3 are the solutes, okay. Maybe I'll mention later, but let us follow what I'm saying. 1, 2, 3. This is. However, before taking up the ternary system, before taking up the ternary system, we shall first consider the binary system, simpler binary system. Binary system 1, 2, 1, 2, and compare the result. There is another hidden purpose. I am give the outline. We have to establish the condition or equation for thermodynamic consistency for the ternary system to find the relation between these two. Okay, this is. But there is another thing that is actually that moves around, or say that is talked about often, Gibbs-Duhem equation. We want to show that we don't, for binary system, no difference between the Gibbs-Duhem equation and equation for thermodynamic consistency. These two are equal, and these two are the same. This will show first. There is no confusion. There is only one. If it satisfies one, it satisfies the other because they are the same. For binary, for ternary, they are different, and it may be needed both are to be satisfied. If a model is to be valid, if I propose a model, if that is to be valid, it must abide by the equation of thermodynamic consistency and the Gibbs-Duhem equation in ternary or quaternary or higher. You know, later on I will show you that Wagner E formalism. Wagner is a great super genius, great man. His formalism is known as E formalism. Unfortunately, is later checked out to be thermodynamically inconsistent. You will be surprised. But it is used. Very popular number one. We'll discuss this, all this. These are all preludes for a greater discussion. But we'll make a compromise that yes, this is very important. This is to be used, but this is an approximation. Why approximation? Why it fails the test of thermodynamic consistency? Wagner formulation, Wagner's model. This was first detected by perhaps Reltn. But we can make a compromise. We can give some justification. We can give some excuse. Oh, well, this is approximation, though, but very close answer. Very small approximation or negligible approximations. Later on, all later on. What I try to tell you, two things are actually floating around. One is Gibbs-Duhem equation, another is equation for thermodynamic consistency. First, we will show the simplest system binary, they are the same. But for the ternary, they are different. To validate a model, both ternary, in case of ternary and above, both Gibbs-Duhem equation and the equation of thermodynamic consistency are to be satisfied. This actually nothing. So let us keep on doing this. However, before taking up the ternary system, we shall first consider the binary system 1, 2, and what else, and compare the resulting equation and compare the resulting equation of thermodynamic consistency compare the resulting equation of thermodynamic consistency, resulting condition, equation is condition of thermodynamic consistency with the Gibbs-Duhem equation for the binary system. This is the introductory statements. Okay. So first we will check up the thermodynamic consistency. You should note that when actually people started talking about of thermodynamic consistency, we are used to Gibbs-Duhem equation. And we are satisfied. Our purposes are solved, solved, and we didn't need anything. But the first striking point is that Wagner's equation, E formalism they call it, for dilute solution. Now I'll give you. Yeah, I've already given, but maybe formula I'll give you. That is not thermodynamically consistent. Then a lot of debates started and etc. etc. So these are actually the thing, system. So start A. I'm writing A because B have A first for binary and B next for ternary. Ternary is our aim. First binary. Let us warm up with the binary and also show in passing that it's same as the Gibbs-Duhem. And we know Gibbs-Duhem. We are very fully aware of the Gibbs-Duhem and we are expert in the Gibbs-Duhem equation. A is what? The equation of title. The equation I am repeating though, but what shall I do? The equation of thermodynamic consistency very good, very good. For the binary system 1 2, for the binary system system 1 2. This is our topic initial. Let us see how we are working. Start. We know, I start with this statement. We know G prime, extensive property G prime is a function of, tell me, function of 100 times I have written temperature, pressure, since binary N1, N2, these are all independent actually. And at a given temperature, and pressure, at a given temperature and pressure, you know what you write? What you write? G prime. What you write? The given temperature and pressure, G prime is these are constant. Given is function of N1, N2, or Bg prime is what? You know, write this out. Del G prime by del N1. We have no N2 times dN1 plus del G prime by del N2 over under constant N1 times dN2. This you know. This is known as what? This is known as what? G1 bar. This is known as G1 bar. You can write this. This is G1 bar dN1 plus G2 bar dN2. These all known to you. You are good. Where you write? Where right? G1 prime is del G prime by del N1 under constant N2 and G2 prime del G prime over del N2 under constant N1. Okay, okay. So you have this because dg prime is a perfect differential. Because dg prime is a perfect differential. Know this? Where you use perfect differential, properties of perfect differential, Maxwell relations. So suddenly actually we have invoked that, call that, okay, in. That is that we have will consider that and utilize this perfect differential properties in the solution suddenly. Yes, but this is actually yes, dg prime is a perfect differential. So what we wrote, remember what is Maxwell relation? What is that? We have what we have using Maxwell type relations, using Maxwell type relations. Relations what? You can write, tell me here, here. dg is vdp minus sdt. What do you get? vdp minus sdt. Recall. dg is vdp minus sdt. Then you have four Maxwells. First one is this. Del v by del t at constant pressure is equal to minus del s by del v by del t under constant pressure is del s by del p under constant pressure. Shall I write this? Del v by del t, del v by del t, del v by del t constant pressure is minus del s by del p recall. Use this. So del g1 prime by del n2 over n1 under constancy of n1. Okay, is what? Tell me. Del g2 over del n1 constant n2. Okay, now replacing, if we replace this is general, so replace g prime by g excess. We are considering excess property. This is the g prime is the total free energy of the system. Extensive. This is also extensive. Excess property. If it is g prime is replaced by g excess prime, then what will g1 bar will be replaced with g excess bar. G1 bar will be and accordingly G1 bar by G1 bar excess, and you could have considered mixing, no problem, no problem, no problem. Mixing property, excess property, a free of the system G, okay, itself as given, okay. Why excess they were considering, sir? Suddenly you are considering excess, not mixing or anything else, or you retaining this. Excess will give us gamma. GI bar excess is RT ln gamma. Activity coefficient. This is about activity coefficients. Ternary interaction. These are about activity coefficients. See, the definition is as you see last log gamma b ln gamma b or log b weight percent by excess and G2 bar by G2 bar excess, and accordingly G1 we have what we have. Write this out yourself. Del G1 bar excess over del N2 constant N1 is del G2 bar excess by del N1 constant. What is the under the constancy, or what? Let us utilize the space. G1 bar excess. What is G1 bar excess? RT ln gamma 1. So write that out. Or RT outside under constant temperature outside ln RT ln gamma 1 over del N2 under constant L1 equals to, tell me, is RT likewise RT ln gamma 2? RT D ln gamma 2, okay, I'll explain this. Del ln gamma 2 over del N1 N2, okay. Noting what you have noted here, GI bar excess is what? RT ln gamma I, which you very well know. So RT ln gamma I, RT outside D ln gamma I, gamma 1, D ln gamma 2. Next what we'll do? RT cancel out. What remains? Give a star here and go to this place. This is not required at all anymore, because we know what is our plan. First complete binary, then take up ternary, and in the binary show that thermodynamic consistency equation that you will find out and the Gibbs-Duhem equation are the same, almost close to that, close to achieving that. Oh well, so let me check it is okay, doing very well. Okay. Start. So we are here. Now the left hand side, we have to walk a little bit on the left hand side as well as similarly on the right hand side. First left hand side. And the left hand side is what? You write nicely. Del ln gamma 1 del n2 under a constant of n. Clear? Very clear. We will stop after 2 hours. No problem. 30 minutes left though. So let me go slowly and no problem. We are not in hurry. Is what? Del ln gamma 1 by del x2. Slight twist. N1 times shall I give or divided by shall I give? Okay. Shall I give you in times? Times will be better. Del x2 del x2 over del n2 times. Okay. Continue. What is this? Right. Utilize the space. Gamma 1 del x2 as you see here. N1 don't disturb here. X2 is what? X2 is what? Del x2 is what? Del is here. Del write nicely. Del x2 is what? N2 by n total. Everyone knows mole fraction over del n2 as under the condition of n1. No problem. Continue here. Left hand side is here. It is better right here. Utilize the space. No problem. Is what? As it is del ln gamma 1 by del x2 under the condition of constancy of n1 times what is this differentiation? What is this differentiation? Where? Where right? Where? Right here. Where? What is NT? Total number of moles is N1 plus NT. We know, write it. No problem. Specify. N1 plus NT. You know though. Is a variable. Variable or not variable? NT is constant. Total moles constant. First line. These are variable. N1 variable, N2 variable. Their sum is also a variable. Okay. So that is N1 is a variable. Is a variable. Variable, dependently variable, but variable. N1 independent, N2 independent variable. N1 is 3, N2 is 5. When this change, total is 8. If N1 is 4, N2 is 6, total is 10. 8 changes to 10 variable, but it is dependent on the value of N1. So that's why N1 N2 only. Okay, but it's a variable. This is variable. Okay, by the way. So what is the result? I am saying all these things is what? Again, how to differentiate this? How to differentiate this? Again, same thing, derivative, ratio, u by v, denominator square is n total, v square, denominator square, suppose call it, call it u, call it v, and this is x, u by v, v square by b times n total, d dx of n2, dn2 of n2 is 1 minus u, second minus u is what? N2 itself. d dnt of n, dn2 of, sorry, del n2 of n total, d dnt of n total. So I am writing here n total. What is this value? N total is what? N1 plus N2. Under what condition? N1. If N1 is a constant, what you have? A constant, then out only D is 1. Let me check it is okay. It's okay. So what you are getting then? Is what? What? Shall I write here? Let us write here. Del n gamma 1 by del x2 times n1. What is this? N total minus n total is what? N1. N total is n1 plus n2 minus n2 by n total square. I am removing this. I am removing this. Let's complete this here. It's better. This line will be completed at least here. Then gradually, what is this? N1 by n total split nt square. N total square. N total times n total. So n1 by n total is mole fraction x1. So x1 outside and put this one next. Del ln gamma 1 by del x2 under the condition of constancy of n1 times what remains? 1 by n total. 1 n total has not been utilized yet. So this is the left hand side. Give a name to this equation. I have forgotten to write this equation. Call this equation please. Equation 1. 1 will be good. And then this will be called this equation 2 that we have arrived at working on the left hand side. Similarly the right hand side. So actually I have to make some room. So I will remove this first couple of lines. I don't need this. These are all next. Similarly, the right hand side is what is here. Write that out quickly. Let us move quickly. Similarly, del ln gamma 2 by del n1 under the constant c of n2 is what? Write this. Del ln gamma 2 by del x1 times del x1 by del n1 under the condition of n2 is what? Write this out. Del ln gamma 2 over del x1 under the condition of n2 times del x1 is what? n1 by n total. We have no difficulty over del n1 under the condition of n2. All set? Okay, I hope I am doing well. Okay, or continue. Just return this as here del ln gamma 2 over del x1 del x1 n2 under n2 times again derivative ratio nt is a variable, so it's not a constant. Okay, so variable. So what is this? What is this? Del nt square denominator square denominator time del n1 by del n1 is 1. Okay, you can write 1, may not write, minus u numerator n1 differentiation of nt by n1. What is the differentiation of n1 plus n2 with respect to n1 under the constancy of n2? N2 is constant, so dn1 by dn1 means like last time, like last time. Okay, is write nicely. Maintain this del ln gamma 2 over del x1 under the constancy of n2 n2. What is this? Nt minus n1. Nt is n1 plus n2 minus n1 is n2 by nt square. So last line is what? You take nt square, break nt times nt, n2 by n total, nt is x2, mole fraction. Write that on the left, on the extreme left, x2. Then you write this one, del ln gamma 2 over del x1 and 2. Okay, copy. And what is left behind? Only 1 nt at the denominator. So times 1 by nt. And given a, what name you will give? Obviously, if this is second, this must be the third, and this is already designated 1. This one. This left hand side I worked, right hand side you worked. So far, so good. Okay, so let's remove this. So from 1, 2 and 3, these two are same, these two are equal, 2 and 3. So from 1, 2 and 3 you should write. From 1, 2 and, I'm very sorry, and 3. From 1, 2 and 3, 1, 2 and 3. What you have? Tell me what you have. Write this. These two are equal, means these two are equal. So write this nicely. x1 del ln gamma 1 by del x2 under the condition of n1 times 1 by n total. This I copied, this, and is equals to this is x2 del ln gamma 2 del x1 under the condition of n2 times 1 by n total, means nt. Nt is n total, t for total. Okay, what shall I do next? What you do? 1 by nt cancel out. So what you have? You remove all these things. Still another space another line you write what you write here. So let me write this. Okay. So what you get finally, write this, or x1 right title del ln gamma 1 del x2 under the condition of n1 is x2 del ln gamma 2 over del x1 under the condition of n2. Will you box this? What is this? What is this? This is the equation of thermodynamic consistency for the binary system 1 2. Binary solution, binary system 1 2. So write this out, call it equation 4. This is our goal. This is the equation of I tell you, this is the equation or condition of thermodynamic consistency. But you will see that this you know already. How do you know? Now this is all looks like it is Gibbs-Duhem equation. Right? Somewhere actually it resembles Gibbs-Duhem equation. So no big deal. Yes, no big deal for binary system. No big deal, Sam. But formally show that I'll do. That this is exactly the Gibbs-Duhem equation. So this part, okay, so this is the equation for thermodynamic. This is the equation for the thermodynamic consistency for the binary system. This is the required equation. This we wanted to find out. So, sir, mention that first. Then we'll compare this with the Gibbs-Duhem and show that for binary there is no difference. And at the same time, we'll note that for ternary there is a difference. And ternary will be taken up after these comments are written here. Then we'll take up the ternary. I don't know, maybe next class. Let us see how much we proceed. So this is, write this out. So this is the equation of, right, equation of thermodynamic consistency for the binary, for the binary solution or system 1 2 and that's it. That's it. One part is over. Next is comparison with the Gibbs-Duhem equation. That's right. Now, shall we remove this? These are all over. So this topic is still there. As I told you, we are in the preparation towards the relation between these two, towards establishing the relation between these two. So this is the thermodynamic consistency equation, and that will do for ternary. This is a ternary system, ABC. That will do later. Then finally we have the relation between these two. I am giving you now. Since actually it's so simple that I should give. They are equal. It can be shown that they are equal. But lengthy. You have to develop this type of consistency equation for the ternary system later on. But few more comments here about the difference between thermodynamic consistency equation and Gibbs-Duhem equation. Comment on this. So let me remove this. Let me remove this. Remove this. You don't need this. Remove. How many minutes left? 10 minutes. So 10 minutes is good enough. Huh? You come back at 2 huh? After 10 minutes. It's okay. Everything is okay here. Lights are on. Okay, 10 minutes that was good enough. I will not proceed anymore. Huh? I'll stop here. You come back. Let's decide. Now, give a star here. Star here. Now what is this next discussion? Gibbs-Duhem equation and this. How different they are? Are they the same? Etc. Now the Gibbs-Duhem equation, quickly. Gibbs-Duhem equation for the binary solution 1, 2. For the binary solution 1, 2 is what? What? In this light, in terms of gamma, what is that? Gibbs-Duhem. Recall binary x1, tell me, d ln gamma 1 plus, tell me, x2 d ln gamma 2 is g. Okay, then next. Quickly, or just little bit manipulate, so that we will actually, so these two are the same. So what is the manipulations are? Or x1, what is this? Okay, x1 d ln gamma 1 by dx2 is x2 times d ln gamma 2 by dx1. Why? Dx2 is nothing but minus dx1. So dx2 and minus dx1. Okay. Go to the other side. Okay. This becomes, okay, since dx2 is minus dx1. If it is minus dx2 cancel, minus to that side, plus, and this come back. Okay, very easy, damn easy. Or what? Okay, this is quality equation 5. Quality equation 5. What is the 4, 5. Now this is actually pitted against this. This is pitted against this. 4, 5 are the same. If it is justification. See here, something here. This is something very important. Note the parts quickly. This is okay. 4, 5 there. They are actually exactly the same. Follow how? Looks like partial derivative. This is total derivative. No one. Partial, particularly partial. But is it really partial? Binary? So that. See, this argument. The partial derivative, note the partial derivative term del ln gamma 1 del x2 n1 on the left hand side On the left, I mean one I am showing. The same logic will apply here. One I am showing that this is not a partial, this is a total, and as good as this. Follow. On the left hand side of equation 4, this part follow here. On the left hand side, this part means this one. Okay, this one. Okay, so this one and this one. So left hand side of equation 4, as I told you, the left hand equation 4 is actually a total derivative. What is the total derivative? D ln gamma 1 over dx2 n1, but this is not at all partial. Why? Dx2, why? Because total derivative, because what is the reason? When you say partial dx del x2, when x1 is constant, partial means something is constant, x1 say. Here in this case x1 and x2 are the computing variables. X1 constant, is it possible? Vary x2 when x1 is fixed in a binary? In a binary, if x1 is fixed, x2 is also fixed. Because x1 plus x2 is a fixed quantity, namely 1. When x1 del x2, it cannot be differentiated with respect to x2, keeping x1 is constant. Impossible. Because when this x1 is constant, then x2 is also a constant. So cannot vary. So because, right, dx1 and dx2 are mutually dependent. So you can fixing the other one, you cannot vary the other. Are mutually dependent. Are dx1 and dx2 are mutually dependent. How are mutually dependent? How? Because how mutually dependent? Are mutually dependent. What is the dependence? dx1 is minus dx2. Dependent. So how can we partial? When partial means others are fixed, keeping something constant. Here x1 x2 are the possible candidates. Dependent. And this comes from where? This comes from where? Following the, this also comes from where? Following the relation, you know, easy. What is the relation? Following the relation, x1 is 1 minus x2. x1 is 1 minus x2 for the binary system 1, 2. For the binary system 1, 2. Very close. That means this as well as these are total derivative. So let us write that is del ln gamma, n1 does not matter. This it leads to x1 also. Del n1 gamma 1 del x2 by n1. I'm sorry. Under the constants of n1 is what you write? D del v. Total derivative is d ln gamma 1 by dx2 and the other one this also del ln gamma 2 over del x1 under the constant of n2 is what? D total. D ln